In the first years of the 20th century, Albert Einstein published his now famous papers on the special theory of relativity. His work helped to shape a new view of what space and time were and how they behaved. Special relativity involves only observers who are moving with constant velocities relative to one another. Recall that constant velocity implies moving with a constant speed in a constant direction. This could involve two observers flying rockets past each other in space. It could also involve an observer standing at a train station while another passes by. Although not typically referred to as laws in the literature, some well-tested ideas behind the theory may as well be. The first is that the same laws of physics describe the outcomes of experiments or observations, regardless of whether they are viewed at rest or moving relative to the experimenter. The second on the list is that every observer will always measure the same speed of light, regardless of the relative motion of the source or observer. This leads to some strange and unexpected behavior of space and time. The third law is the equivalence of mass and energy. It says the energy and mass are interchangeable. That is, mass can be converted to energy, as in nuclear power plants and in the cores of stars. Energy can also be converted into mass. This can happen when the kinetic energy of high-speed particles in large particle accelerators is converted into new particles with large masses. Another feature that can be seen, when the equation is rewritten, is that the more energy a body has, the more mass it has. An important feature of special relativity is what is called the equivalence principle. It states that there is no experiment that can reveal whether a system is stationary or moving with a constant velocity. That is, an experiment done on a train station will behave the same as it would aboard a fast-moving train. Thus, the whole question of whether one is really moving or who is really moving becomes irrelevant. Of course, in daily life, there is definitely a practical sense of what we consider to be moving and what is at rest, but in a strict physics sense, there is no difference between these two cases. Equivalence principles like this have been around since Galileo, but Einstein's version includes electromagnetic phenomena as well. The theory makes some interesting predictions about the behavior or time, length and mass. Before discussing the strange predictions of relativity, it is important to understand that each person will observe his or her own time, length and mass as normal, regardless of any motion. It should also be pointed out that these effects are only noticeable when extremely sensitive measuring instruments are used or when the speeds involved are nearing the speed of light. The faster the relative motion, the greater these effects. When two observers are moving relative to one another, they will disagree about how each is measuring time. Each person sees his own clocks running as they normally would, but each sees the other's clocks running too slowly. This effect is called time dilation. Each observer will disagree on lengths of objects or distances between events. Objects moving along with me look normal, but those same objects moving with the other observer look shorter along the direction of motion. That is, if the other observer held a yardstick out in front of him, pointing along his direction of motion, that yardstick would appear to me to be less than 1 yard long. If I were holding a yardstick out, the other observer would see my stick too short. Each of us sees the other's length shorter. This effect is called length contraction. Lastly, there would be disagreement about masses. I possess a certain amount of mass. However, someone moving relative to me would measure that I actually had more mass, even though I would measure myself as having the same mass as always. I would in turn measure the other observer's mass increased. The faster something moves, relative to an observer, the more mass it has. If the speed of a moving object approaches the speed of light, the mass approaches infinity, as shown on the graph. Thus, no object with mass can travel at the speed of light. It would take an infinite amount of force or an infinite amount of energy to do so. Thus, the speed of light is the speed limit of the universe. Thanks to Einstein's work, and the work of physicists before him, we now understand that space and time are constantly adjusting in a way that the speed of light is always the same for all observers. Because of its unexpected predictions, it has been one of the most tested and best verified theories of all human knowledge.